All right, this concept is looking at kind of derivatives as rates more generally. So not talking about um, kinematics or things that we've talked about before. We're talking about just the general derivatives as rates. And if you have a derivative, what does that kind of tell you about the thing it's describing? So this should be hopefully pretty much review, but it'll also help kind of solidify maybe some weak spots for you. So derivatives as rates. If you remember, derivatives calculate the rate of change of one variable or quantity with respect to another. So we've talked about, for example, velocity being the rate of change of position with respect to time. So that's one variable with respect to another. But you need to be careful when describing rates because if it's the rate of a rate, you need to specify that. So in this example here, f of x describes the rate of people entering the store with units of customers per minute. What does f prime of x describe in this context, and what units will it have? So f prime of x is the rate of change of the rate at which customers enter. So you'll notice it's the rate of a rate, so I need to specify both of those in there. And it will have units of customers per minute. Is that, yeah, that's our units. Per minute, because customers per minute is the rate, this rate right here, the rate of customer, the rate that customers enter. And then this second per minute is saying it's the rate of this first thing per minute. Or you could say that it's the customers per minute squared. And this is something that I notice with many students when they give you this on the AP test, because they often give you, here's a rate, find the derivative of it, what's that? And they're looking specifically, do you realize that it's the rate of a rate, and therefore it should have this squared denominator term. So we've talked about that kind of in general. Now let's talk about it more specifically. So the units will always be the x, or the numerator, value units divided by the, sorry, that's completely wrong. Let me restart that. It's always going to be our y value units, or, you know, the function, the output units of the function, divided by the x value units, which is the input to the function. So if you have v of t, whatever the units for v would be your y values. Whatever your units for this t would be your kind of x or input. So as an example, if x of t is position as a function of time, then we have our x units and we have our t units. X is meters, t is seconds. So x prime of t has units of meters per second. V of t is the velocity as a function of time. The velocity units are meters per second. The time units are seconds. So v prime of t has units of meters per second, which more commonly will be presented as meters per second squared. So here's a quick example of where we might use this with other rates. So what is the rate of change of the area of a circle with respect to its radius? Well, let's start with what is the area of a circle? It's pi r squared. And if we want to find the rate of change with respect to the radius, we need to take the derivative with respect to the radius. So let's take the derivative of both sides, and we get dA by dr. In other words, the derivative of area with respect to radius. That's what this literally means here. And that's going to equal d by dr of pi r squared, which will equal 2 pi r. So that is the derivative, the rate of change of area of a circle with respect to its radius. And kind of preempting some stuff that we'll talk about later, this kind of makes sense if you think about it, because if I want to make the radius of a circle ever so slightly bigger, what am I going to do? I'm basically just going to add this very thin line right around the outside edge, right? You know, a thin line right around the outside edge. And how much area does that have? Well, it has a length of 2 pi r of the circumference and a width of, you know, essentially nothing. So it's going to be kind of the area that we get is 2 pi r length with an infinitesimally thin radius. And so that's how much we're adding as r gets bigger. So that covers rates of change that are kind of the general form.